for the afternoon session. Thank you very much.
Thank you. So we have, I think we have the 4 presenters, so you can just share your screen and start with your poster pictures. So I think Roman is around, I guess. Oh, he was.
Yeah, I should be.
Yeah. Hello, how are you doing?
I'm doing well. Let's see if I'm smart enough to share my screen. That's always a big if. Okay, how does that look?
Yeah, perfect. Thank you.
Okay, cool. So I'm Roman Yampolsky, and I have this 73-page monstrosity paper about controllability of AI. I was able to squeeze it into a workshop paper of about 8 pages, which was later compressed into a poster of 1 page, and now it's a 3-minute demo. So let's see if I can make you interested enough to read the actual paper. The question I'm looking at is a fundamental question, in my opinion, of AI safety. Can we succeed? First, I try to define what AI control problem is, and then I'm trying to see if anyone was able to prove mathematically, or at least rigorously argue, if it's solvable, unsolvable, undecidable, and maybe formalizing it a little more will help figure out what's going on there. So one thing I do is I try to break down different types of control. Then people say, okay, we're going to control AI. What does that mean? There is direct control, where you give orders to the AI. You say, okay, stop the car, and the car stops immediately. Whatever it's in the middle of a highway or in dangerous hours, doesn't matter, the car follows orders precisely. Then you have, on the opposite end of this extreme, what I would call delegated control, where the system is super intelligent, you are the dumb human, and the system decides for you what needs to happen. So you say, okay, car, pull over, and the car says, oh, no, we're going to the gym instead, you need to lose some weight. So that's kind of the opposite end of it. And then there is 2 kind of in the middle approaches, where either the car is, or AI in general, attempting to align with your preferences. It has a good model of you. It understands what you want and why, and attempts to guess from your, again, ambiguous human language, what it is needs to happen in this situation. There are other possibilities. People talk about merging with AI, so some sort of hybrid system. And we can also look at that. There are some additional problems with that as well. But in a paper, I try to look at each possible meaning of control and see what the problems are. We know about explicit control having problems with the so-called genie problem, where no matter what you wish for, you're later going to regret it greatly. Problem with complete delegated control to this wise advisor, ideal advisor, is that you no longer make any decisions, right? Someone else makes all the decisions. You become like a child, like a baby, where your parents know what's good for you and make all the decisions for you. So the hope is that either we can get someone much smarter than me to actually prove that I'm wrong and it's possible to solve one of those control problems, or we need to concentrate on some sort of trade-off between complete autonomy of a system and capability. So we want AI systems obviously to help us. AI is incredibly useful. We want help solving problems, but we want to remain in control while getting all those benefits. So hopefully that's interesting, and maybe you'll show up for my poster presentation. Thank you.
Thank you, Roman. So now we are having Tom.
Yeah, 1 second. I will try to share my screen, but I can't since someone else is still sharing his screen.
Roman, can you stop sharing your screen?
Theoretically, yes. In practice, let's see.
Okay, let me try if I can. I have some powers, but
you have some power to kill it for me.
Yeah, I have the power. Okay.
Excellent. So you're in control.
I use my
that's
power.
Delegated control. Otherwise,
okay.
Take over.
And now, Tom, I think you can do it now.
All right. Okay, let me know if you can see it. Does it work?
Not yet for me.
Okay, 1 second. Yeah, maybe it doesn't work. Can you maybe pull up my slides? Or is that possible?
Yeah, maybe Huáscar.
I will share your presentation 2. Just a second.
I'm sorry, I'm on my iPad and it doesn't appear to be working.
Yeah, no problem. Opa. Sorry.
Okay, perfect. So thank you very much. And I will be presenting our paper on domain shifts in reinforcement learning and how to identify disturbances in the environments of RL agents. So next slide, please. And I want to start with a short example, the classic Walker 2D from OpenAI, and a slight modification of it where the floor is green. So now, if we assume that we trained a reinforcement learning agent in the original environment, so the one on the left-hand side, then the green floor on the right-hand side is just an illustration of things that might change during the deployment of our agent in the real world. So the change could either be only visually, but it could also mean that the dynamics change such that the grass is now, the floor is now grass and not concrete anymore, and or other things that could just change during the deployment of our agent in the real world. So an interesting question we could ask ourselves if we could call such a change out of distribution or actually in the distribution of settings where we want our agent to function properly. And whereas in other domains such as computer vision, out of distribution is typically pretty well defined, or we can define it very easily. We struggled with this and other notions in reinforcement learning on even simple examples like this one. And that's why we decided to investigate this topic a bit more deeply. So next slide, please. And what we found is that in the world of reinforcement learning, there are actually many terms related to this problem in one or the other way. But clearly distinguishing between all of them is not always entirely straightforward and doesn't often help too much. So for example, we could frame the problem from the beginning as a distributional shift problem, as an out of distribution instance, as a transfer learning problem, or even as a robustness problem, depending on our interpretation of the problem setting and also on the interpretation of the definition of the term we are using. But often, yeah, this doesn't really help us. And that's why in this paper, we propose a slight different formalization of problems that are more fitted to the RL setting. So next slide, please. And for this, we turn to the very classic formalization of reinforcement learning problems via the Markov decision process. So this is the standard setting for most RL problems we can see today. And it's just a tuple of states, actions, a reward function, a stochastic transition function, and an initial state distribution. And this actually allows us, next slide, please, to form the one before. Those were two. Okay, thanks. Yeah, and this simple definition or formalization allows us to compare two different tasks or two different Markov decision processes, A and B, via the aspects that build up this Markov decision process. So the state space, the action space, the reward function, the transition dynamics, and the initial states. And to show you what this means, I want to show you an example. So next slide, please. And for this, we considered in this paper the simple, very, very simple warehouse domain where an AGV has to move towards a goal while avoiding obstacles or hitting any objects. If we consider this agent is trained in a setting without any special cases and things that occur, we could define things that happen during the deployment as out of distribution, domain shift, as transfer learning problem, or we could instead isolate any disturbance during the deployment into aspects of the MDP. And for this, on the next slide, we have a short overview of how this could look like. So for example, if you consider again this AGV in this setting where it has only seen boxes and a very limited world, then if there are suddenly workers interacting with this AGV this would manifest as a change in the state space and the transition function. Or noisy sensors, on the other hand, would only be in the state space, or functions of the AGV only in the action space and the transition function. So to wrap this up, what does this really give us? On the next slide, there's a lot of existing work going under different names and making different assumptions, tackling the problem of trying to compare environments, or the training and the testing environment, from different angles, and applying general formalizations into the RL setting is not always straightforward or helpful. Whereas decomposition of complex problems into aspects of the Markov decision process is straightforward, because it's already the tool of choice for all or most of all RL problems. And it actually helps argumenting safety and to compare different approaches from different angles. And it is only also a first step towards isolating disturbances for further safety analysis. But that's actually what we're trying to look at in our future work, and how we can detect things that are out of distribution within specific parts of the MDP. But we say that, we believe this is a helpful aspect towards separation of concerns and safety in general. Yeah, thanks. That's actually it.
Thanks,
already.
Tom. Okay, our next speech, I think we have James Miller around.
Yes.
Can you share your screen? Yeah, hello.
Okay, how is that? Can you see it?
Yeah, perfect. Thank you.
Oh, excellent. Well, thank you. I'm Jim Miller, and there's an approach to AI safety called the Oracle approach. And the idea behind the Oracle approach is that, if we create a superhuman intelligence, an AGI, we limit its ability to only answering questions. So we put it in a cave, we don't connect it to the internet, and we ask the questions: how do you cure cancer? How do you stop global warming? And it gives us answers. Now that might not work, and we, the authors of this paper, we completely admit that. But let's say it does. We are able to limit an AGI to just answering our questions. It, of course, could still do us enormous harm. It could say, hey, this is how you cure cancer, but in fact, it secretly is telling us how to build a virus that will exterminate humanity or something. So this paper, we said we want to test out if we can handle untrustworthy oracles. And to do that, we should take advantage of the fact that we already have superhuman intelligences in very narrow domains, such as chess. I'm sure you're all aware that the best chess programs are vastly better than what humans could do. So what this paper proposes, we haven't done it yet, and we have no intent, we don't have the capacity to build this. We hope perhaps someone listening does. What we'd like to do is create two classes of chess oracles. One will give you advice and will be really trying to help you win. The other will be trying to help you lose, but it'll be deceptive. It won't just suggest stupid moves, let your queen be captured. It'll be suggesting moves that look really good, but in fact, if you play them, you'll find you lose. It'll decrease your chance of winning. So we'll create these two classes of chess oracles, and you'll be either getting advice from both and you won't know which is which, or maybe you'll just be giving advice from one and you won't know if you're playing with the helpful or unfriendly chess oracle. And the idea will then be to see, can you come up with strategies to determine which oracle you're playing with? And can the friendly oracle come up with strategies to prove that it's friendly? So one strategy might be the friendly oracle will say, well, look, I know this is the best move, but I can't prove to you that. I can't explain it. This is beyond your intelligence to see why you should move your pawn this way. But I could explain why you should move your knight this way, and it's not as good, but it's worth it. Now, the unfriendly oracle will be trying to break into that and stop you from doing that. And hopefully there'll be interaction between these oracles, and maybe we'll come up with consistent strategies to be able to figure out how to handle untrustworthy oracles. And if this works in chess, we could expand it, create oracles in other domains where we have superhuman intelligences, like Go, or solving some kind of math problems. And we'll try to see, are there approaches we can use, perhaps using like signaling theory from game theory, where we can handle potentially untrustworthy oracles that are smarter than us. Maybe not. And of course, if we can't handle unfriendly chess oracles, there's no hope of us handling unfriendly general intelligence oracles. So we would at least learn from this approach what's not going to work. Again, the team that developed this paper, we are not intending on developing a chess oracle. So if any of you are capable of doing it, we would be absolutely thrilled. Thank you very much.
Thank you, James. And our last pitch of the session comes from Ian Banerjee. Please go ahead.
Can you see my screen?
Yes, you just set it in and present as view.
Yes. Okay. You can hear me properly, right?
Yeah, perfectly.
Okay. So our work, we are focusing on AI systems which require user interactions. So these are the most practically deployed systems are AI systems that require user interactions. And the user is in two roles here. One is the user is part of the system, and another is the user is also observing the AI system from outside. So there is a bidirectional user experience problem. And an example here is a closed loop control system, artificial pancreas, where the user is getting insulin injection from the artificial pancreas. So the user is the system itself, as well as the user is interacting with the software. So there are two roles of the user. Now, what we want to do is we want to make this autonomous software that is there in the AI system accountable. And accountability in this case means three things. One is that as and when the user's requirements change, the system should be safe. And even if the system is safe, or in case of failures of safety, the system should be able to explain why the system failed. So in that case, there are two other aspects of accountability. One is interpretability, where whatever decision the system is taking, you have to be able to explain why that system took that decision. And also transparency, which means that you should be able to look at the data coming out of the system and figure out what went wrong. So we want to incorporate this in the linear design space for software design. So typically the software design that we have seen comes from figuring out technical gap, then we have regulation and standards, requirements, design, implementation, and then finally deployment. And there is very little feedback from deployment back to design. There is feedback, but it takes a long, long time. So we want to make this a circular system where the feedback is fast and we can do accountability. So one of the problems, if we don't have these three properties, is that there is a disconnect between what the user thinks the system is going to do and what the system is actually doing. So in the AI terms, it's a very common term. We call it mental models. Right? So the user has a mental model of the AI system, what the AI system should do, and the manufacturer of the AI system has a different concept of the user's mental model. So when these mental models clash and they don't match, that's when there are problems. So for example, one of the problems we are looking at is phantom meals, which means that in an artificial pancreas system, which is controlling your insulin while meal intake, if your insulin injection is not enough, that means you are going to hyperglycemia, glucose level is rising too much, then what the user tends to do is specify false meals. That means they're saying that we are taking a meal, but they are not really ingesting it, but they are just saying it so that the artificial pancreas will give them insulin. So this can cause safety risks, and there is no way to predict whether these kind of things will occur in practice. So what we want to do is when such things happen, we want to figure out why it is happening. And one of the main reasons is that the mental models are not matching up. So we want to incorporate this right at the design time in a circular fashion, not in a linear design process that is traditionally taken up. So the main idea is we need to incorporate the mental models in design process, and the mental models can be changing over time. So so the main idea is that we have to extract the mental model that the user is using to interact with the system, utilizing the data that we see that is coming out of the system. And the problem is very difficult because not everything that the system does is visible to visible in the data, right? Because the data is being monitored in a very limited sense. There are only limited sensors that we can use to monitor. But if you want to extract the mental model, then there are a lot of unknown variables and parameters in the system. So if we want to really do safety analysis of an AI system and make it accountable, then we always given with a problem that is underspecified. Right? We don't know the entire system, but we are still trying to explore and extract things from that system. So we are proposing to learn mental models of the user from the data, but it's an underspecified system. So now there has to be a information sharing between whoever is trying to do the safety verification and the manufacturer, because it's an underspecified system. We need more data, but data may not be given to the manufacturer, or data may not be shared between the manufacturer and the safety verifier, because there might be rules in place. So the overall problem that we are trying to solve is what is the optimal set of information that needs to be shared between a manufacturer and a safety verifier, so that we can enable safety verification and accountability in the AI software. As well, there is less cost of the manufacturer for certification of these devices. So that is our whole research direction that we are taking. And more information is there in the poster. So if you come to the poster, we can discuss in more detail.
Thank you, Ian. This is the last pitch and the last presentation of the session. Thank you very much to all the participants, panelists, and of course our invited speaker. And